compressive sensing work, really, is the idea of incoherence and randomness. And so, what in a compressed sensing, in a general compressive sensing data acquisition protocol, what we're going to do is we're going to acquire a signal about X, a signal X of interest, an image, a 1D signal, a video, whatever, by actually collecting linear measurements about X. And we're going to collect little n of them. Okay, so we're going to collect n samples about X, which are linear in X. And so in the compressed sensing protocol, what you want to do is you want to have these sensing waveforms AJ to be as spread out or incoherent as possible. Okay. And so, as I explained on Monday, but I realized lots of you were not here on Monday, what you can say about is to take this AJ to be white noise. So this is a completely crazy proposal in compressive sensing that to acquire an image, to acquire a signal, the idea is to correlate this signal with white noise. So what is the idea underlying compressive sensing is that the signal is extremely local, because it's sparse like this. The measurements are the opposite. They're extremely global. They're extremely unlocalized. And there's a very simple reason for this, is that if the signal is sparse in the time domain, let's say this is time like this, I cannot acquire the signal by subsampling in time, because, well, if I subsample in time, I'm going to have to skip points, and then I could skip spikes. But if now, instead of sampling in time, I sample in the domain which is incoherent with time, like for example the frequency domain, then all of a sudden I can skip a lot of samples. So the basic picture is something like this. We have a very localized signal. And what we're going to do is we're going to correlate this very localized signal with very global measurements in such a way that when I look at the dot product between this and this, in any coefficient, it has a little bit of information about all the locations where the signal is non-zero and about the amplitude. Okay, so each measurement picks up a little information about each component. So what is kind of a foundational result in the field of compressed sensing is that, well, we've got the classical viewpoint, which is, I think, is personally extremely problematic, where basically, what do we do in life, right? And that's kind of what I explained on Monday. What you do is you build an enormous number of sensors, you acquire an enormous number of data points, or data bits, and as soon as the data collection is over, you throw away most of it for compression or transmission, for storage or transmission purposes, because you apply data compression. And so this is extremely wasteful. Why do you want to acquire so much data when you know ahead of time that you're going to throw most of it away? Okay, and that's really the classical viewpoint where you really measure all the data, all the pixels, all the coefficients, you sample the signal at a very high rate, if you will. And as soon as you're done with the sampling, you throw away most of what you've seen because of redundancy. Okay? So in the compressed sensing point of view, what you do is you measure everything and then you compress it down. In the compressed sensing world, you don't do like this. You take n random measurements by essentially correlating X with white noise, for example, and you reconstruct by N1 minimization. And the surprising result of compressive sensing is something that looks like this, is that if I look at a number of data points that I'm acquiring here, which is k times log n, or even smaller than this, k times log n over k, where k is a number of coefficients I will keep in my compressed representation, then after compressed sensing protocol, I have a smaller error. The compressive sensing error is smaller than what I get by collecting everything and keeping the most significant bits. Okay, so, all right, so let me make sure that we all understand what the result is saying. It's saying, okay, what I've got is I've got a signal, okay, and it has components like this. And what I have is, well, if I can only store k coefficients, and I want to have the smallest distortion, these coefficients are going to have to be the largest. Okay, so this is the representation which uses k pieces of elements, a block of information that is the closest to X in an L2 sense. Okay? So now suppose that what do we do in real life roughly? What we do in real life is we acquire the entire signal and then we compress it. And now the kind of the staple for compression is something like this. Compressing means set to zero all the small stuff and quantize the big stuff. That's really what we do. And so what I'm going to say is well, we're going to have this vector xk, which is simply the signal where I set to zero all the small stuff but keep the k largest coefficients. Okay? And so when you go through this very wasteful acquisition process, what we do is you acquire everything, you see everything, and then you keep the k most significant pieces of information, which are the largest coefficients. But to know what to keep, you need to see everything. Right? Otherwise, what do you know? In compressive sensing, you just don't do this. What you do is you sample the signal holistically by correlating it with white noise. And then you solve a minimization problem. And what you guarantee is you're going to have a reconstruction if you take k log n sample, which is as good as knowing ahead of time the amplitude and the location of the k largest coefficient. And that's really the main message underlying compressive sensing. Okay, so in mathematical terms, what we can see is something like this. This is now I sample a signal by essentially sampling the Fourier coefficients. Okay, so I've got y equals ax. A is again a matrix that looks like this. It's a partial discrete Fourier transform with randomly selected entries. And what a recent result with a graduate student Yannick Candes says is that if I keep a number of Fourier coefficients, which is k log n, then the compressed sensing with probably x hat minus x is within a constant of x minus x, had I known ahead of time all the largest coefficients and their locations. Okay, and this is kind of answering a lot of things, because when you work on real systems, which we do, a lot of people would say, well, what if the signal is not sparse? Well, when the signal is not sparse, when the signal is nearly sparse, this is very small, because x is well approximated by its k largest coefficients. So this is going to be very small. And when it's not sparse, well, this is not so small, because the signal is not compressible, and therefore you cannot really approximate it by just a few data bits. Okay. Now, one thing which is very important is that, of course, this compressed sensing theory would be completely irrelevant if it were not robust to noise, because in any real-world system that I'm familiar with, we have noise, and so we have to deal with it. So if the signal is a reconstruction that is highly dependent on the 6 digits in your measurement, you'd be in really great trouble. Okay, but it is not, and so when you have noisy data, well, you could try to recover the signal by something that looks like this, where you try to trade off, but now you would not exactly enforce the quality constraint. So now when you have noise, it makes no sense to enforce that the recovery must exactly match your data. You're going to have to relax this constraint, and so you're going to say that, well, I want that it matches approximately. So you're going to replace this by a constraint that looks like this, so ax hat minus y in L2 is less than some tolerance delta. So we want that the recovery be within the noise level, or in Lagrange form, you would want to minimize something like this, which is statistics known as a lasso. Okay, and so when you've got a result like this, then what you can show, and maybe I will not discuss this as much as I did on Monday, you're showing that compressed sensing is really stable when you have noise, and you can get a mean squared error of recovery, which is essentially optimal, and you would, in many ways, you would not be able to improve it by any method whatsoever. Okay, so when you've got, in just a few words, I think what I want to say here is that when you've got noise, you've got a recovery that degrades very gracefully with the noise level. Nothing goes wrong. Okay. All right, so the kind of the general formulation of compressive sensing is that all of what I've talked about applies if we use as sensing vectors that are sampled from a population F, So what I have is I have a bag of sensing vectors. This could be the sinusoid, in which case I would do Fourier sampling, but it can be any population F. And so all of the stuff I talked about apply as long as you take sensing waveforms that are sampled independently at random from a population F that obeys two very simple properties. One is that the covariance matrix of this population is not rank deficient, and the second is this incoherence property that you want your sensing waveforms to be spread and not localized. Because if they were localized, there is no way I can subsample. Okay. Okay, so the surprises underlying compressive sensing is that the sensing is ultra efficient, it's non-adaptive, as I discussed before. You make no effort to understand the signal. You just correlate it with random waveforms that have been chosen independently of the signal, and that you can recover the signal by tractable optimization. And why is it that people are excited about this? Excited about this because there was this dogma, as I mentioned before, and that's what everybody does in signal processing, where you acquire lots of data, and then you throw away lots of data to just keep the most significant bits. And what compressive sensing is, instead of, it completely bypasses this wasteful acquisition process by just getting the important bits at once. All right, so one of the most successful applications of compressed sensing is in the area of medical imaging. And so this is the experiment we've seen before. Here, the image is not sparse, but the gradient is sparse. So what you do is you minimize the L1 norm of the gradient, because as you can see, this is an image which is piecewise constant, so it has a very sparse gradient, and so the recovery just said, well, minimize the L1 norm of the gradient, and so this kind of experiment we did in 2004 now is really well understood theoretically, because it says, well, I've got an image, I've got very few coefficients about it, but its gradient is very sparse, so when I'm going to minimize the L1 norm of the gradient, which is a total variation norm in image processing, I'm going to get perfect recovery, and that's what we see. Okay. All right. So I'll show you just one application area. They made many, many others, and there are many groups around the world who apply compressed sensing in medical imaging, especially in magnetic resonance imaging. I'm going to highlight the work of Lustig, Pauly, and Basanawala from Stanford University, because this is the work I know best. But you should know that, if you go to an MR conference, most of the talks are about this subject. Okay. All right, so let's kind of look at Michael Lustig's beautiful point of view on MR. Okay. So Michael Lustig works in pediatric MR, and so here is really an area where you really need to speed up the acquisition process, because children cannot stay still in a scan. And so children will move, like imagine to put a 2-year-old child in a scan, they will move, and therefore you're going to get very blurry images. Now this can be more serious than just having, 8-year-old child like on this thing that is moving, so when you look at the scan you cannot see anything. For example, there was a story that was reported in a Wired magazine which was something like this. You had a 2-year-old boy that had received a laser transplant, but the results of medical tests were really alarming. And so something needed to be done because this guy was not doing well at all. So he came to Stanford Hospital with a very alarming test. And so for the doctors to see what was wrong, you need a very high resolution scan. Now the problem with the high resolution scan is that, at least for this 2-year-old boy, was that it would take 2 minutes. Now imagine what it takes to stop breathing for 2 minutes so that you can, you have to take a single breath and be still for 2 minutes. But you cannot do this. Especially a 2-year-old boy that cannot do this. So what a doctor would have to do then is to stop respiration for 2 minutes. So when you stop respiration for 2 minutes, that is, you deprive oxygen in the brain for 2 minutes, the least of your worries may be your liver. Now, with a compressed sensing strategy, you can reduce perhaps this scan time from 2 minutes to 10 seconds, or 15 seconds. And so maybe you could actually stop respiration for 10 seconds, without suffering from appreciable oxygen loss. Okay? And so that's the kind of the work that Michael Lustig is doing. His observation, which is absolutely correct, is that MR is not used in child pediatric. It should be used, but it's not used because the scan time is too high. It's too large. Okay, so by applying techniques of compressed sensing, these groups of researchers, John Hawley, Michael Lustig, who you can see here, Vasanawala, have been able to show that you could clinically reduce scan time by 8x without loss of resolution, really. And so they've produced some spectacular results where they would take, and these are now clinical results, where they would take 6-year-old children or 8-year-old or 2-year-old children, go through 8x acceleration that have a scan time which is 16 seconds instead of 2 minutes and something, and still get pictures that show exquisite details by using the sparsity prior for the recovery. Okay, so I hope that this image will show well, but this is what you would get in a conventional CS, in a conventional MR, and here is what you would get by accelerating this 8 times and using the compressing sensing recovery. And so I hope that you can see on this picture that you see white dots, which is what doctors are very interested in because these are the lesions that they're looking for, which are hardly visible here. So Michael Lustig and his colleagues have been, so this is for a 1-year-old female with liver lesions, which is those little white spots that you see here. Oh, okay. All right, great. So we're going to be at the movies. Okay, so you see these white liver lesions that you can see, and it goes 8 times faster than this, by the way. And then this is a 6-year-old boy now, 8 times acceleration. The kind of stuff you're interested in is the liver again. The kind of stuff you're interested in are those veins, the hepatic vein that you cannot see here. I can see it on my computer screen, but it's here, but on the screen it doesn't show.